Okay, seriously, you guys, this is one of the most important lessons to ensure that you are successful for the rest of the school year. This is the one. So you have that periodic table with you and those worksheets, because we're going to embark in something that it's not so much that it's big, but it's the foundation of everything else. It's what you need to go forward from here. So it's important. Before we dive into the actual lesson, I want to go over a couple of key ideas that really serve as a backdrop. And those you'll find in your reading in the text. One of them is the law of definite composition. And in layman's terms, or just everyday language, it basically is just talking about the fact that if you have a chemical compound, it's always got the same composition. If we take a look at water, it's always H2O. It's not H3O. It's not H2O5. It's not H4O. It's H2O. So if you look at the way water exists and you focus on this word mass, you can look at the periodic table and we have that average atomic mass. And if you recall, oxygen is a 16, and then when we look at the average atomic mass of hydrogen, it's a 1. There's 2 of those, so 1 plus 1 is 2. So we're talking about a mass of 18. We'll just say units for now. And so if that is the case, then any sample of water anywhere is by mass going to have a ratio of 16 per the total of 18 of that mass coming from the oxygen, and a ratio of 2 to 18 coming from the hydrogen. Basically, in a nutshell, we're just saying that water is always going to have the same composition as any other sample of water. If it had a different composition, it wouldn't be water. Period. Done. The other one, the law, that they sound sort of similar, the law of multiple proportions. What that's talking about is the fact that you can indeed have 2 elements that form more than one compound. Here they're talking about 2 forms of iron oxide. We call the first one iron Roman numeral 2 oxide, and then the second one is iron Roman numeral 3 oxide. You'll learn later what those formulas mean. Another example of that would be we have carbon monoxide, we have carbon dioxide. And the idea here is, yes, 2 elements can form more than one kind of compound, but each of those compounds will have a definite composition. So even if there are multiple proportions that 2 elements can bond in, each compound still follows this. Okay, so that's what those are about. Background information. And here are 3 terms that aren't really the heart of what we're doing right now, but you're going to hear me refer to them sometimes because they're a part of our topic. And when we look at these 3 things, they all have something to do with the way an atom attracts electrons. And the first one is called electron affinity. That word affinity means attraction. If you have a strong affinity for someone, it means you're kind of sweet on them. You have an attraction for them. So an electron affinity has to do with an atom's attraction for electrons. And it's measured in a way that it reflects the amount of energy released when an atom gains an electron. Now, when we talk about releasing energy, that means that the atom is going from a less stable state to a more stable state by releasing that energy. Kind of like if you were in an agitated state and you kind of calm down because that situation of agitation is over. Now you're at a lower energy level, and that's actually better for you. That's the analogy we want to think about for that for now. So electron affinity, it has to do with the attraction that an atom has for electrons. Ionization energy, what that has to do with is the energy required to remove an electron. So if it's very difficult to take an electron away from an atom, then it would have a high ionization energy. If it's really easy to take an electron away from an atom, which is the case for metals, we know that what do metals do? They give away electrons. So if it's easy, which means it doesn't take a lot of energy to remove that electron from an atom, then it has a low ionization energy. When you look at the periodic table, sodium, we know that what it does, it has one valence electron, tends to give that electron away, and so it's going to have a low ionization energy. It's not going to take a lot of energy to remove an electron from sodium. But on the opposite side of the periodic table, if you look at fluorine, how many valence electrons does fluorine have? 7. And so fluorine is really going to tend to gain an electron to create that octet, which we know is stable. So it's not going to be easy to remove an electron from fluorine, because what it's going to do instead is gain an extra electron. It will have a very high ionization energy because it's not giving up electrons. It's going to take electrons from something else. So when we move across the periodic table from left to right, the ionization energy increases. Electronegativity is really, in a lot of ways, you think of it as something so similar to electron affinity, but it's different in that it's really referring to a different kind of chemical bonding. And as you learn about chemical bonding, you'll understand this part a little better. But it's the measure of an attraction that an atom has for a bonded or shared pair of electrons. Again, electronegativity and electron affinity, they are both measures of how great an atom's attraction for electrons are. And so those are some words that you'll hear me use. These 3 definitions, understand, are not the main point of the lesson, but you're going to hear them. So we must move on. So the big idea here, compounds are formed when elements bond with other elements. And there are 2 kinds of chemical bonds that we're going to be learning. And here is a list of what you need to know about each of these types of bonds. This is going to be something you're going to want to go back to before a test. See if you can answer each of these things. Can you describe how the bond occurs? Can you explain what categories of elements are bonded in this way? Can you state the category word that we use for those compounds that are formed from the type of bond? Can you describe the type of matter that's formed, general properties of that type of matter? And then the one that we're going to spend the most of our time on is writing names and formulas for these compounds. So the first type of chemical bond that we're talking about here is called an ionic bond. And an ionic bond has something to do with ions. We've been spending some time talking about ions. And an ionic bond is formed when there's an electron transfer. One atom gives away 1 or more electrons, another atom gains those electrons, and so oppositely charged ions are formed. A positive and a negative is going to be attracted to each other, and then we have what's called an ionic bond, and therefore an ionic compound. So the name of the type of compound that is formed with ionic bonds is ionic compounds. That's easy to remember. Ionic, ionic. What kind of an element gets involved in this type of a bonding situation? We're talking about a metal and a nonmetal. Why? Because we know that metals will lose electrons, nonmetals gain them. They form ions. The other type of bonding is called a covalent bond, and that's when electrons are shared between two atoms, and those, in that situation, your electron clouds overlap, so you have sharing of electrons between the two nuclei. Here's a nice diagram of that. And when this occurs, the type of compound that is formed is called a molecular compound. And that happens when nonmetals bond with other nonmetals. Now remember, nonmetals are the ones that have a tendency to gain electrons. So they have a greater electronegativity. And as they are attracted to electrons, what can happen then is these electrons, both of these atoms are attracting those electrons and they end up sharing them. So that is what we want to think about when we think about a covalent bond, and the type of a compound is called molecular. So here's a little brief summary of a little bit of that information that you need to know. What type of elements get involved in an ionic compound? Metals and nonmetals. Nonmetals bonding with other nonmetals will always form the molecular compounds. And then the other thing you want to understand is what kind of a structure is formed from these two different kinds of bonds. And in an ionic bond, what you end up with is called a crystal lattice network, or a crystal. They do not have molecules. This is going to be a stray from what we learn in elementary school. In elementary school, when we write sodium chloride's formula, we call that often a molecular formula, because in elementary school we don't want to make it too complicated, do we? But the truth is, this is not a molecular formula, because salt doesn't have molecules anyway. Mind blown, right? No molecules. Well, it's a crystal, and crystals don't have molecules. So when we talk about a covalently bonded compound, like water, our old friend water, here two nonmetals bonded together, they do form molecules. The difference is that when you're talking about a molecule, every H2O unit is its own little entity. There's different molecules. But here, when we talk about a crystal, it's different than a molecule. We're going to be focusing on ionic compounds for a while, because that is the group of compounds that we're going to learn names and formulas for first. So to recap what we've seen so far, ionic compounds are made of ionic bonds, made of ions. Metals lose electrons, nonmetals gain electrons. And so when you look at what this business about a crystal is, what you have here is an electrically neutral combination of positive and negative ions. Now what this particular drawing represents would be sodium chloride. And so what you have here are these green circles are representing our chlorines. There they are. And then the little purple ones are our sodiums. Now, when I say to you that these are not molecules, you have to understand that we can't really find a molecule here. We can't say, well, here's a molecule of sodium chloride, because this chlorine becomes an ion, which we call chloride, is bonded to this sodium just as much as it is to that sodium, as it is to this sodium. There's a sodium behind it, and if this was continuing to form as a crystal, then off the screen there'd still be another one, sodium here, there'd be another sodium out here. This chloride is equally attracted through positive and negative charges that attract each other to all of these sodiums. Over here, this sodium is no more or less attracted to this chloride as it is this one, or this one, or this one. This sodium is attracted to this chloride, this chloride, this chloride, and this chloride equally. So you can't find a molecule there. That's a crystal. It's a repeating pattern of positive and negative ions in a crystal. So since there are no molecules, when we write the formula, we call that a formula unit. That's our representative particle here. We call this we can just call it a formula. That would be okay. But we don't want to call it a molecular formula, because that's not exactly true. There's no molecule. You'll be reading about the properties of ionic compounds in Chapter 3 as you do your text reading. Here's an overview of them. Ionic compounds are crystals, so they tend to be hard and crunchy. There's a regular repeating arrangement of ions in that crystal. The bonds are very strong, so ionic compounds tend to be more difficult to crush than a covalently bonded compound. Their covalently bonded compounds can be stretchy, and ionic compounds aren't. They're rigid, so they're not elastic or stretchy, they're rigid. Ionic compounds tend to have high melting points. They're often soluble in water because they have those positive and negative charges, and you know, of course, water's polar, so it'll be attracted to charges. And ionic compounds are solids at room temperature. So when we look at this formula unit, here's a formula unit for a compound that we call lithium fluoride. Lithium fluoride. What it is it's the simplest ratio of positive to negative charges in that crystal. Crystals of ionic compounds are characterized by a regular arrangement. They have well-defined regular shapes. For example, here are some gemstones. This one's quartz up here. This is pyrite. A lot of you will know what that is. That's what people call fool's gold, because it kind of looks like gold, but it's certainly not, and it's not valuable. So people would fool people into believing they were buying gold when they weren't. They were purchasing a mineral called pyrite. These are some lovely amethyst crystals, the purple. And then here are some basic mineral crystal shapes. And table salt, which we refer to as halite sometimes if you're coming from a geological point of view, the mineral name is halite. Table salt crystals really are square. If you look at them closely, they're squarish, okay? Because of the way the positive and negative ions are arranged, they actually have a cubic shape. Different ionic compounds have a more complex arrangement of those positive and negative ions in that crystal, and that's where you get some more complex shapes. In our class, we don't need to memorize any of these crystal shapes, but they are pretty interesting, and this is a nice little chart I found from of a pretty neat website called Geology Cafe if you want to look for a good resource for earth science ideas and topics. It seems like they have there. Um, so here again, in an ionic bond, we've got this crystal. This one is lithium fluoride, and they're showing how those are arranged in that crystal. And then on to where we need to be so we can do our homework. We need to know some very specific rules about ions that, having done your previous work, what we did last week, this is not going to come as a surprise to you. But on your periodic table, what you want to do is above hydrogen, write down a +1, because hydrogen's column, when those atoms become an ion, they become a +1 ion. That's what they do. Above beryllium, write +2. Remember we talked about groups and families? All of these elements in beryllium's column have 2 valence electrons. They give away 2 valence electrons to become a +2 ion. That's the rule. So write that above your column for beryllium. With the noble gases, we know that those don't react, so we don't have a rule for them because they don't become ions. But fluorine, chlorine, bromine, and iodine, which we call the halogens, those are always a -1 charge. So you write that on your periodic table above fluorine. And then oxygen's column, they become a -2 charge. Nitrogen, notice we're talking really about just the nonmetals. This is our division between metals and nonmetals. We don't want to forget that. So nitrogen's column of nonmetals become a -3. And then for our class, there are 3 other elements that you have to know what the charge is. And I want you to write in the box, not for the whole column, aluminum is a +3. Find aluminum. It's a +3. And then go diagonally. Zinc is a +2. Write that in the box. And then silver's a +1. Those are 3 rules that you're going to have to know. Some of the other elements in the middle have a specific rule, but those are the 3 you're going to be responsible for. You're going to know that aluminum is always a +3 when it becomes an ion. Zinc is a +2. And silver is a +1. So make notations on your periodic table. And then we're ready to move on. Our skill that we're learning today is going to be writing correct ionic compound formulas to reflect that formula unit. And we know it's going to be electrically neutral. What does that mean? It means for every positive charge, there is a negative charge. You've got your worksheets with you. We'll look at some examples. If we have a compound called sodium chloride, which you're already familiar with, how would we figure out what the formula for sodium chloride is? We would look on the periodic table, we'd find sodium, we'd see that it's a +1. We'd look on our periodic table, we'd find chlorine, it becomes an ion called chloride. We change the name of the ending of that negative ion so that the reader knows that this is an ion. This is a compound now. And we see a +1 will cancel out a -1. For every positive charge in a crystal, there's going to be a negative charge. So we know that they're going to react on a 1-to-1 ratio. And so we write down NaCl to reflect that ratio. What if we have a compound called barium iodide? Again, chemistry's a language. Iodine, when it becomes a negative ion, we call it iodide. The ending of a negative ion changes when it becomes an ion to IDE. So what would be our formula? We would look on our periodic chart. We'd find barium. We'd see that it's in the positive 2 column. We find iodine. We see that it's a negative 1. Now, in that crystal lattice network, every positive charge has to have a negative charge. So one iodide with a negative 1 is not going to cancel out both of the positive charges that barium has. One iodide ion is not sufficient to cancel out those charges. So a second iodide with a negative 1 is needed. With 2 iodides, we'll have enough negative charges to cancel out both of those positive charges that barium is contributing. So what do we have for a formula? We're looking at 1 barium and 2 iodides. So that's where we get this formula. BaI2 is the correct formula unit, or just we can just say the correct formula for barium iodide. Another example, how do we get this formula for calcium selenide? We look at the name, we look up calcium, we see on the periodic table that it's a positive 2. We look up selenium, which is the selenide, we see that it's a negative 2. Positive 2 cancels negative 2. Calcium ion's going to have 2 positive charges. A selenide ion is going to have 2 negative charges. They cancel each other out. That's electronically neutral. So with 1 of each, we have a formula. Magnesium nitride, how would we get from a name to a formula? We're going to look on the periodic table, find magnesium. It's a positive 2. We look and we find nitrogen. It's a negative 3. You can see I'm just going to draw lines to cancel out. Positive 1 cancels a negative 1. Positive 1 cancels a negative 1. With my sketch, I still have a negative charge there. So I need to add more positive. What I'm working with is magnesium with a positive 2. So I'm going to add another one. Each magnesium has 2 positive charges. Well, that positive is going to cancel with that negative. But now I have a positive charge here without a partner. So now I'm thinking, hey, I need some more negatives. What am I working with? Nitrogen. It's a negative 3. So I'm going to add in another nitrogen. It comes with 3 negative charges. My dashes are meaning these little negative charges. So now this negative charge cancels that positive charge. But now I have these 2 negatives. They don't have anything canceling them. So now I think, oh, I need some more positive. I'm going to put another magnesium in. And look what happens. We have all of our positive charges canceling the negative charges. Now here's what you want to see. We've got 1, 2, 3 magnesiums, and we've got 1, 2 nitrogens. So 3 magnesiums, each contributing a positive 2. That meant there was 1, 2, 3, 4, 5, 6, right? There was a positive 6 charge. And then there's 2 nitrogens, each contributing a negative 3. 2 times negative 3 is negative 6. So the charges are all canceled now. Once the charges are canceled, I'm really not interested in thinking about the charges anymore. I have a formula which reflects how many atoms are in, how many ions really, are in that crystal lattice network. That crystal for magnesium nitride, for every 3 magnesiums, there's going to be 2 nitrides. So take a look at your worksheet, the one that has the square boxes and the circles on it, the front one. And you've got 3 questions at the top. Ions are held together in ionic bonds by what? Well, there's that strong attractive force between positive and negative ions. Opposite charges attract. You should be able to answer number 2 and number 3 on your own. And then we're going to go to number 4. Now, what they've given us here is they've given us the charges. So we don't have to look on the periodic table to know what the charges here are. This is kind of like a worksheet with training wheels. They're giving us charges. So number 4, what would the formula look like if we have barium with a positive 2 and oxygen with a negative 2? Well, can positive 2 cancel out negative 2? For every positive charge, we need a negative charge. Absolutely. So we just need one of each. And that's our formula. Number 5. We have barium with a positive 2 bonding with fluoride, which has a negative 1 charge. Is a negative 1 charge sufficient to cancel out a positive 2 charge? There's barium. I'm going to put the 2 positives in. I'm going to draw fluorine and give it a negative charge, just 1. And then we're going to connect those. Well, I still got this positive charge that doesn't have a partner, so I need to add in a second fluoride with a negative. Those 2 charges cancel. And what I'm really interested in is how many bariums did I use? 1. How many fluorides did I use? 2. So my formula reflects how many ions are in that crystal. Potassium chloride. You try that one. We've got a positive 1 and a negative 1. Let's look at number 7. We've got sodium, which is a positive 1 charge, and we're putting it together with phosphorus, which is a negative 3. So if we need a drawing, oh, that doesn't look so good there. We've got sodium, and it has 1 plus. Each sodium has a positive. Each phosphorus has 3 negatives. A charge of negative 3. So I can connect these 2. They cancel each other out. But I have these extra 2 negatives. So I'm going to add in another sodium. Each sodium has a positive 1. That gets rid of that one. And now I need a third positive. and that's going to cancel. And now I'm going to count how many ions did I use. I used 1, 2, 3. Of my positive ions, the sodiums, and I used 1 phosphide, which is my negative ion, my anion. And so Na3P is my formula. Now, for my visual learners, I like to draw these out, but not everyone will feel like that's useful. Some people tend to think more about math. So they're going to look at number 9, and they're going to say, well, if I have a positive 2 that I need to cancel, here I have a negative 1. How many of these negative 1s do I need to cancel out a positive 2? 2 of them. And they're going to go ahead and write that in, MgI2, magnesium iodide. Here with number 10, if I have a positive 3 and I have an anion that provides a negative 2, how many of each do I need to form a neutral compound? Again, you can think about this the math way. Well, clearly you need more negatives. 2 times negative 2 is not going to work out just to cancel positive 3. But if you take 2 times a positive 3, 2 times 3 is 6. And then you take 3 times the negative 2. 3 times negative 2 gives you a negative 6. So we're going to need 2 of our positive 3s and 3 negative 2s. Some people like to do that, just thinking about the math that way. Other people like to draw a little picture and see those charges cancel. One of the things I want you to notice is, look what happened. We have a positive 1 and a negative 3, 1, 3, and we have 3, 1 in our actual formula. Are you seeing this? 1, 3 gave us 3, 1. Look what happened here in number 5. 2, 1. In our formula, we ended up with 1, 2. The numbers that we're looking at, they reverse. 2, 1 gives us 1, 2. In number 10, 3, 2 gives us 2, 3. The numbers that you're looking at reverse. If you look at numbers 11 through 15 on your worksheet, all they're asking you to do is to look at the actual formula and tell how many you see. So in number 13, where it says Be beryllium, you're looking at the formula. You see a 3 there. There are 3 berylliums in that formula. How many phosphorus are in that formula? You look at the formula, 2. So 11 through 15, we don't need to spend a lot of time on. Take a look at number 16 through 20 now. Now what they're doing is they're going to make us do a little bit more of the work. They're going to make us look up the charge on the periodic table. So for number 16, lithium. Look on the periodic table. What is the charge of lithium in an ionic compound? It goes by the location. You wrote the +1 above that column. What about sulfur? What is the charge of sulfur in an ionic compound? Then you're going to write your formula for lithium sulfide, which would be the compound name. 1, 2, let's practice with the reverse. 1, 2 is going to give us 2, 1. 1, 2, 2, 1. It's going to take 2 +1s to cancel out that -2. You try number 17. Look up the charge on the periodic table. And now, let's think about that formula. Number 19. You look up the charge. Don't wait for me to give you this answer. If you don't take the time to look on your own and you rely on me, you're not getting the practice. So seriously, take a look at that periodic table. Okay, +3 will cancel -3. So we need one of each. Having your periodic table with you for your homework assignments is going to be imperative. You will quickly have memorized where these charges are because you're going to do your own work. And as you look at the periodic table for those charges, you're going to find that you will quickly know them. Again, it's really easy to use the pattern that we're observing as a shortcut. If we're writing these formulas, we look up the elements that are involved in a compound like magnesium chloride. Magnesium is a +2. Chloride comes from chlorine, which is a -1. We copy the symbol, and then we're going to do any kind of thinking about the math and how things cancel. We're going to do that with these charges. And we think about how, okay, oh, that's good. Not a good M. We have a +2. How many chlorines with a -1? I'm going to put that in red there. Oh, sorry. We need 2. What I really want you to notice is that when we look at that, those numbers switch. That +2 ended up here. The negative 1 ends up there. Not with the charges, but the numerical numbers that you use at the end. 1, 2. Again, aluminum bromide. Look up aluminum on the periodic table. Look up bromine. You have a positive 3 and a negative 1, and those numbers switch. And the formula is aluminum with a 1 and aluminum and bromine with 3. Now, do we write this? Have we ever included ones? Let me do that in black. Think about that. We never put a 1 in, so those are assumed. Here we have positive 2, negative 3. The numbers that are in your charges switch for your formula. So your formula, 3, 2, 2, 3. Oh, I did that backwards, I'm sorry. 2, 3 becomes 3, 2. So with that information, you should be able to do part A on the back of your worksheet there. And this time now, they're just giving us the name. So now we have a little more work to do. We need to find the symbol. This is why we spent so much time with flashcards. Let's look at number 4. We look up beryllium. What's the symbol? You don't know the symbol, you're going to go slower. It's going to take you longer. And then what's the charge? What negative ion or atom that we know becomes a negative ion could be sulfide? Well, you look at the root word, sulfur. It's a negative 2. Where am I getting these numbers? I'm looking at the periodic table at the numbers I just wrote down on there. So a positive 2 and a negative 2, they're going to cancel each other out. So my answer notice I'm not keeping the 2's in there. The formula is the smallest whole number ratio of positive and negative ions in that crystal lattice network. So positive 2, negative 2 cancel each other out. It's a 1-to-1 ratio. Let's look at number 6. I still have students who are looking for sodium as a capital S. This scares me. This is why we did flashcards. Sodium. What is its charge? Positive 1. Oxide comes from oxygen. Negative 2. 1, 2. We reverse that. It's going to take 2 positive 1s to cancel out a negative 2. 1, 2. 2, 1. We don't put the 1s in our formulas. Also notice when we're talking about an ion with a charge, we write that charge in the superscript position. When we are writing a formula, our numbers in a formula go in a subscript position. This is important. You're learning a language. You're going to have to be able to do the grammar on this language. What's the charge of aluminum? What's the charge of oxygen? 3, 2, you switch the numbers, reverse them. 3, 2 becomes 2, 1. So, does that work mathematically? Sure. 2 times 3 is 6. And 3 times 2 is 6. 2 times 3 is 6. 3 times 2 is 6. So 3, 2, 2, 3. The reverse shortcut works. So I'm going to let you work on part A, but I want you to, you can either stop, you can work on that for a few minutes, then listen to this. It's up to you. But part B has a twist. So we have this formula, copper chloride. We're going to look up copper on the periodic table. Uh-oh, it's not in an area where we have a rule. What are we going to do? I guess we can't do our homework because we just don't know the charge of copper. We can find chloride coming from chlorine, and we know that that's a -1. Well, we may not know what copper's charge is, but the name gives it to us right there. The Roman numeral is there because we don't have a rule for copper. Copper doesn't have a specific rule for its charge. Sometimes it's a +1. Sometimes it's a +2. So here in number 1, copper's a +1. +1 cancels with -1. Our formula. But sometimes copper can be a +2, as in number 2. Copper Roman numeral 2 chloride. The Roman numeral gives you the charge of the metal. So in number 2, now copper is a +2. Chlorine hasn't changed. It's still a -1. Oh. 2, 1. We reverse them. 1, 2. It's going to take 2 of these -1s to cancel out that +2. We just switch those numbers. So if you look at your periodic table and you look at that transition metal section, think about that D section, SP, D, and F. Many of those metals, they don't have a steadfast rule for what charge they're going to take when they become a positive ion. So for that reason, we have metals that we call multivalent, which just means in everyday language they can have more than one charge. Sometimes copper's a +1. Sometimes it's a +2. Technically, ladies and gentlemen, part B is easier than part A because you only have to look up the negative ion to see the charge if you don't remember it. You have the charge of the positive ion right in front of you because that is what the Roman numeral gives you. Let's look at number 4. I'm going to erase some of this. What Roman numeral is that? And what is the symbol for 10? For some of you, that's a big question. 10 with a +4. And then chlorine hasn't changed. It's still a -1. So how many -1s will it take to cancel out a +4? 4, 1, 1, 4. There's our formula. So part B, super easy. You're going to do the same thing that you did in part A, only the Roman numeral tells you the charge of the metal. Notice all ionic compounds are written metal then non-metal. It's always positive then negative. Always. Grammar rule. You're learning a language. Do not go on to part C. Don't try it. We'll talk about that later. That's just there for later so that you'll have all three types of things in one page as a reference, but do not go on to part C. We have copper here. The positive 2. What does phosphide come from? Phosphorus. Look at the periodic table. What is the charge of phosphorus when it becomes an ion? It's a negative 3. 2, 3. 3, 2. Formula's done. You can complete these. Now on the next sheet in your packet, you get to do the same thing, only you're looking at it a little bit differently. Here, they're giving you the symbol and the charge. You're going to write the formula and you're going to name it. Why is this so important? Because the negative ion has an ending that is different than what that element was called when it was an atom. Fluorine becomes fluoride. Nitrogen becomes nitride. Let's do number 2. We have the two charges, 2, 3. That part, if we rely on the reverse, we just switch them. Now we have to name this. I hope you remember or kept your flashcards, because if you do not know the symbols for your elements, it's going to slow you down and you're going to spend way too much time on your homework assignments, and tests are going to be a disaster. So here we have tin, and we have nitrogen, which becomes nitride. And tin, notice where it's at on the periodic table. It's over here. Oh, new color here. It's over here. We don't have a rule for that, so we're going to go ahead and put in our Roman numeral 2 in the name. For silver, notice the plus sign doesn't have a number next to it. If there's no number, it's automatically a 1. Chemists are kind of lazy too. They're not going to write those 1s in because it's assumed. So silver's a positive 1, which you can see that was one of the ones you marked on your periodic table that you need to know. So we have a 1 and a 2. One, 2 becomes 2, 1. And then we're going to name it. Change the ending to IDE. Excuse me. The ending of your negative ion always changes to IDE. Now we are going to see that on this worksheet, the ones that I have an asterisk there for you is a hint for you, because those are going to require a Roman numeral in the name. And try to figure out what Roman numeral goes in the name. For some students, that's a struggle, and we have a whole nother mini lesson we'll do just to make sure you're able to do that well. Here we're getting the big picture, so if that's a struggle for you, don't panic yet. But you're going to write the formula and then the name. So here for number 6, 2, 1. Remember that negative doesn't have a number, it's a negative 1. 2, 1 becomes 1, 2. I'm using the reverse, the switch rule. And this is zinc iodide. Copy the name of the element, that's the positive, which we call a cation. And for the anion, or the negative ion, we change the ending to IDE. Now, with some of these, like nitrogen, it's difficult for students to know, right, where am I going to cut that off and put the IDE? Like, could it be nitrogide or is it nitride? Honestly, you learn that by seeing it and hearing it. You learn it by reading the correct word and hearing it. It's nitride. Phosphorus becomes phosphide, not phosphoride. It's phosphide. Speaking of phosphide, this is beryllium phosphide. Beryllium phosphide. Yes, you're going to need to consult your periodic table for spelling a little bit. It's right there for you. Do your own homework. The more you do your own work, the more familiar this stuff becomes, and then you're not sweating it on test day. On the bottom part of that page, here they're giving you names, and you're writing the formulas, which is really what we did in part A of that previous worksheet. So this is just more practice for you. I'm going to let you work on that, and then we will see you in class soon.